It was the year 1828. A Norwegian priest, Hans Morten Trane Esmark, picked up a heavy black stone on an island somewhere near Breivik and sent it to one of the most famous chemists in Europe, Jons Jacob Berzelius. When he found an undiscovered element in that rock, he named it after the Norse god of thunder, Thor, and it came to be known as thorium. He had used the name once before in 1815 for something that turned out not to be an element at all. For the next 70 years, nobody knew what they were holding. Thorium dioxide had the highest melting point of any oxide we know of, so its first real job was glowing inside gas lamp mantles, and only in 1898 did Gerhard Karl Schmidt and Marie Curie find that it was radioactive. Ever since, nuclear scientists have studied thorium and thought of it as the answer to almost every problem. Cheaper fuel, less waste, and reactors that cannot melt down. So why in 2026 do we still not have one single commercial thorium plant on the planet? To answer that, let's go back to Oak Ridge, Tennessee in the 1960s, and to Alvin Weinberg, who ran the lab there for 18 years. There he was convinced that fuel rods sitting in pressurized water were the wrong design entirely. In 1965, his team switched on the molten salt reactor experiment, which had no fuel rods at all. The uranium was dissolved straight into molten fluoride salt and pumped around the core like very hot water. It became the first reactor in history to run on uranium-233, the fuel you make from thorium, and ran until December 1969. This reactor never actually bred thorium, it just proved the engineering. The machine that was supposed to start breeding thorium at scale was the next step, which never actually happened. The Atomic Energy Commission backed a rival design, and in 1973, Weinberg was pushed out of his own laboratory for refusing to stop arguing for his design. But thorium has had its way of fighting for its place, mainly because it's about 3 times more abundant than uranium. And even then, the uranium that we're after, uranium-235, only makes up about 0.7% of what we mine. Compared to the specific isotope that we burn, thorium is hundreds of times more available. Meanwhile, the OECD's Red Book puts identified uranium resources at a little over 135 years of availability at today's consumption rate. And that could decrease drastically once data centers start bidding for their own reactors. Now the problem is that thorium is fertile rather than fissile. The difference is that fissile materials can directly sustain a nuclear chain reaction by splitting when being hit by slow neutrons. Fertile materials, on the other hand, cannot split easily on their own, but they turn into fissile materials after absorbing neutrons inside a reactor. So you hit thorium-232 with a neutron and it will not split, just absorb the neutron and become thorium-233, which has a half-life of about 22 minutes. So it decays into protactinium-233, which takes another 27 days or so to become uranium-233. That is a breeder reactor. Each fission gives you a little over 2 neutrons, one to keep the chain reaction alive, one to convert another thorium atom, and if you hold on to the fraction left over, the reactor makes fractionally more fuel than it burns. Now here's where molten salt starts to come in, because doing that with solid fuel rods is close to impossible. Because fission products build up inside the rods and soak up the neutrons you need, the rods end up getting thrown away with usable fuel still inside them. Dissolve the fuel into liquid salt and you can filter that waste out while the reactor runs. The Danish company Copenhagen Atomics is the most visible attempt at this, with a layered core that they call the onion core. This is the uranium salt in the fuel layer, heavy water in between to slow the neutrons, and a thorium blanket outside where the breeding happens. Liquid fuel changes the safety maths too. A molten salt reactor runs at atmospheric pressure, and if it overheats, a frozen plug at the bottom melts and gravity drains the fuel into shielded tanks where the reaction stops by itself. But the most advanced thorium reactor on the planet is Chinese. At Wuwei in Gansu province, the Shanghai Institute of Applied Physics runs a 2 megawatt molten salt reactor called TMSR LF1. And on the 1st of November 2025, it confirmed thorium to uranium conversion inside an operating core. A 100 megawatt demonstration plant is targeted for 2035. Copenhagen Atomics has 2 full-scale non-nuclear prototypes built, and Switzerland's Paul Scherrer Institute will host its first real chain reaction. And India, which has staked its nuclear strategy on thorium since the 1950s, cleared stage 2 of that plan on the 6th of April 2026, when the 500 megawatt prototype fast breeder reactor at Kalpakum went critical. Thorium will be stage 3. But there are caveats with thorium, and they are significant. Nobody yet has hit the milestone that actually matters. A breeder has to make more fissile fuel than it burns, a conversion ratio above 1, and China's reactor has been reported at around 0.1. Also, thorium does not actually free you from uranium. Due to its fertile nature, even thorium reactors need a starter charge of fissile material just to get going, and the only options are uranium-235, plutonium, or uranium-233 you bred somewhere else. None of those are easy to supply. The Oak Ridge record also gets remembered more fondly than it deserves. As the Bulletin of Atomic Scientists documented, that reactor shut down 225 times in 4 years, and only 58 of those times were planned. Its special alloy cracked when it touched the fuel salt, graphite swelled, tritium leaked, and the cleanup cost dozens of times what the reactor cost to build. There is a weapons problem too. Uranium-233 comes out contaminated with uranium-232, which throws off gamma radiation fierce enough that thorium's defenders count it as a built-in safeguard. It also forces remote handling, thick shielding, and reactors that cannot be serviced once switched on. Protactinium causes trouble inside the reactor too because it absorbs neutrons. Leave it sitting in the core and it will swallow the very neutrons that were meant to breed fuel. So an efficient thorium reactor has to keep pulling it out. And that's the weak link because protactinium is chemically very different from thorium and uranium and comparatively easy to separate. Pull it out, leave it alone for a month, and you're left with uranium-233 clean enough to be weapons usable. So the chemistry that makes the fuel cycle work is also the chemistry a bomb maker would want. And then there's the boring reason, which is probably the most significant. Uranium is cheap, and its supply chain took 70 years and enormous public money to build. For thorium, there is no mining industry of any size, no fuel fabrication chain, and no regulator anywhere with a finished framework for licensing a reactor whose fuel is liquid. Copenhagen Atomics was widely reported to fire up its first chain reaction in 2026. Its own roadmap now points it at 2028 for this, with commercial units produced in early 2030s. The physics has been sound since the 1960s, and the Chinese result is real progress on a technology that has sat idle for half a century. But thorium has never been held back by physics. It has been held back by economics, by regulation, and by the fact that the world built its entire nuclear industry around a different element, and until now never had a good enough reason to fork out the expense to rebuild it. What is different now is that demand for firm, clean, always-on power has gone vertical, and for the first time in 50 years, somebody might be willing to pay for that rebuild. Berzelius named this element after the god of thunder in 1828. We've seen the flash, but as of now, we're still waiting for it to make the noise.